One question that you might have after reading through the first section, and you should read through the first section before watching this video. So if you haven't yet, go ahead and do that. But one question I thought you might have is about complete graphs. So I'll just take a couple minutes here and talk about complete graphs. So complete graphs are defined by letting there be n vertices. So let's say the complete graph of order n. So remember that means it has n vertices. Has every pair of vertices as an edge. So its edge set is the complete list of pairs of vertices. So complete graph of order n, we often denote this as kn. And so the first thing I'll do here is just draw the first, 6 complete graphs. So K1, and we start with n greater than or equal to 1. Otherwise, we wouldn't have any vertices, and that doesn't really do anything. So K1 just has one vertex. There are no pairs of vertices here, so K1 is just an isolated vertex, also known as the trivial graph. So let's write down. So it has order 1 and size 0. So K2, that means we have 2 vertices. Remember, the subscript here on K is telling me how many vertices there are. So K2 has one edge because there's just one pair of vertices. K3, I have 3 vertices. And again, every pair of vertices is an edge. So there are 3 edges here. Some notes on K3, right? This is sometimes called a triangle, or a 3-cycle, or a cycle of order 3, are all different ways that we can call this complete graph of order 3. K4, and I'll actually do a couple different drawings of K4 here. So here's one drawing that you'll see in the text. And I want to, so we can count the edges here. There should be 6 of them. One thing I'll say about this, one thing to point out, notice that a couple edges in K4 intersect, at least in this drawing. That does not mean that there's a vertex there. Just because 2 edges cross each other does not necessarily mean there's a vertex there. If I wanted to put a vertex there, I would draw a dot or an open circle there to indicate that there's a vertex. And then it wouldn't be complete anymore if I did put that vertex there. So again, just because edges cross doesn't mean there's a vertex there at their intersection point. We'll get into crossings of edges later. Good question is, can we draw graphs without there being crossings of edges? And so another drawing, and I'll say here, we haven't defined isomorphisms, but I'll say this here. This is isomorphic. It's the same graph as this one. And we can know it's the same graph because I'm drawing every single pair of vertices as an edge. So here's another way I could draw that. Notice this one doesn't have any crossings in it. So that's kind of a nice drawing of K4. So K4 has 6 edges. Moving on, K5, I'll draw that one. And maybe I'll go up to 6 here. So K5. Again, I'm drawing every pair of edges. You can count that I had 10 edges here. K6. By the way, here's a good question for K5. Can you find a drawing of K5, right? Can you move around these vertices to avoid any crossings? Notice we have lots of crossings here. 1, 2, 3, 4, 5 crossings in this drawing. Can you do a drawing without any crossings, or can you minimize the amount of crossings in a drawing? Something to think about if you want to play around. And we'll talk about that later for sure. So now I'm drawing K6. Again, every pair of edges, or every pair of vertices is an edge in this graph. And there we have K6. Now, how many edges does K6 have? Well, we have to count these, or we can start conjecturing on a formula in general and think about this combinatorially. I have 6 vertices, and every pair of vertices is an edge. So how many pairs of vertices are there? You should remember from some basic combinatorics that this is the same as 6 choose 2. So 6 vertices, and I want to know how many 2-element subsets there are, because each one of those is going to be an edge. So this is 6 choose 2, or 6 times 5 over 2, or 15. So K6 has 15 edges in it. So in general, and I just wanted to talk about this, in general, Kn has size n choose 2, because n choose 2 is the number of 2-element subsets of an n-element set. Since we have n vertices, and every pair of those vertices, every 2-element subset of those vertices is an edge, there's exactly n choose 2 edges. N choose 2 has a nice common formula, n times n minus 1 all over 2. So that's complete graphs and why they have the size that they do. All right, see you later.